Hello students, how are you all? I hope you all are doing good. So we are back again with the next lecture, with the chapter which was magnetic effect of current. So in the last class, we already learned a new concept which is known as electromagnetic inductions, in which what we were doing, we were producing the reverse process. Yes, we were producing the electric current with the help of magnetic field. That is by the process which is known as electromagnetic induction. So today we are going to see three things. These are the important things in this chapter which we are going to study in today's lecture. Let's see what is in the box. Yeah. So see, these are the topics. First, we are going to see Fleming's right-hand rule. We have already seen a rule which is known as Fleming's left-hand rule, which was giving the direction of force acting on a current-carrying conductor. Yeah, direction of magnetic force acting on a current-carrying conductor. So there is a rule which is known as Fleming's right-hand rule. Then we will see a device which is known as electric motor, and then we'll see electric generator. So these two topics we are going to cover today. Now let's start with the Fleming's right-hand rule. So what does this Fleming right-hand rule give? This rule will give you basically the direction of induced current. This rule will give you direction of induced current. What is induced current? We have already seen in the last class. Whenever there is change in magnetic field with time, then that will produce an induced potential difference. And due to that induced potential difference, there will be a current generated in the conducting loop. That is known as induced current. So the Fleming's right-hand rule will give the direction of that induced current in the circuit. So what does this rule say? Again, this is similar to a Fleming's left-hand rule. The only difference is that the nomenclatures are something changed here. So if you stretch the three fingers, that is thumb, index finger or forefinger, or you can say middle finger or second finger. Yeah. So thumb, second forefinger and second finger. So if you stretch thumb, forefinger and second finger of your right hand such that they are mutually perpendicular to each other. You can see they are mutually perpendicular to each other. That is, from any side you can see they will be perpendicular to each other. You can see from any orientation they will always be perpendicular to each other. So that is known as mutually perpendicular to each other. So what does Fleming right-hand rule says? If you stretch the forefinger, thumb and second finger of your right hand mutually perpendicular to each other, and if forefinger is representing the direction of magnetic field, if forefinger is representing the direction of magnetic field, yes, forefinger representing the direction of magnetic field, and thumb is giving the direction of motion of conductor. Yes, thumb is giving the direction of motion of conductor. Then what we will say, this middle finger will give you the direction of induced current. This middle finger will give you the direction of induced current. Yeah. So here, see this. Stretch the forefinger, second finger and thumb at the right angle to each other. The forefinger represents the direction of magnetic field, direction of field. Second finger represents the current. Okay, so this I think misprinted. This is a printing mistake. This is actually left-hand rule statement. So what does this right-hand rule says? This is of left-hand rule. These nomenclature are of left-hand rule. I think these are misprinted. So see, what does this says? If you can see here, this is correct. In the right-hand rule, thumb is representing the direction of motion of the conductor. Forefinger is representing the direction of magnetic field. Then this middle finger will give you the direction of induced current. Middle finger will give you the direction of induced current. So what does we write? Thumb. Starting with thumb, thumb will give you the direction of motion of conductor. Direction of motion of conductor, any conductor which is moving in a magnetic field. Then what is forefinger? Forefinger will give you the direction of magnetic field. So if we get the direction of motion of conductor by the thumb and direction of magnetic field with the help of forefinger, then second finger, or you can say middle finger. Then second finger on middle finger will represent the direction of induced current. So that is basically Fleming's right-hand rule, which gives the direction of induced current in a conductor. Clear? So I hope this right-hand rule is also clear. Okay. Now let's see, this is the important concept, or this is the important part, which is known as electric motor. Electric motor. So all of you have heard about this word? Yeah. It is pretty much useful in everyday life. Yeah. It is used to lift the water. Yes. And what I can say, in the electric fans, refrigerators, MP3 players. Yeah. In everything, electric motor is present. In everything, a device known as electric motor is always present. So what is the basic functioning of a device or of electric motor? That it converts electrical energy into mechanical energy. What it does, it basically converts electrical energy into mechanical energy. That is the basic concept you can see in this definition also. An electric motor is an electric machine or a device. You can also say a device. The electric motor is an electric machine or a device that converts electrical energy into mechanical energy. That converts electrical energy into mechanical energy. Clear? So what is basically happening here, it is working on the principle. Now we have seen what is electric motor. So it works on the principle that whenever a current carrying conductor is placed in a magnetic field, then a force, or you can say magnetic force, will act on it. Force on magnetic force will act on it. So that is the principle that we have already seen. Yeah, that whenever a current carrying conductor is placed in a magnetic field, then a magnetic force will act on it. So electric motor works on this principle. So as you can see in this diagram, what is actually happening, there are two magnets, north pole and south pole of a permanent magnet, and there is a rectangular coil like this, which is rotating in this magnetic field. Yeah, which is rotating in this magnetic field, and the external connection is also there. This is a battery. The current is flowing through this coil and it is rotating. So what you are doing, you are providing the electrical energy with the help of battery, and what you are getting the rotation of the coil. You are getting the rotation of the coil, or you can say you are getting the mechanical energy. You are getting the mechanical energy by just providing the electrical energy. So that is the basic concept on which electric motor works. So now you can see most electric motors operate through the interaction between motors magnetic field. So there is some interaction between motors magnetic field and electric current. Due to that electric current in a wire and motor's magnetic field, there is something known as force generated, or you can say magnetic force generated in the form of torque. In the form of torque applied on the motor shaft. So whenever there is any torque present, or whenever there is torque produced, so there is some shaft connected to this coil. There is some shaft connected to this coil, which will convert this electrical energy into mechanical energy. Which will convert this electrical energy into mechanical energy. So that is the basic principle on which electric motor works. So now we will see in detail that how this actually works. So there is something we are drawing here. This is a rectangular coil. Suppose this is a rectangular coil. Okay. This is a axle, suppose. Yeah. What you can do another type of thing. There is a thing which is known as split ring. So this is a coil which is rectangular coil A, B, C, D. Suppose name it as A, B, C, D. And we are keeping this coil in between are two strong magnets. One is north pole and one is south pole. And the direction is such that this length or the line of the coil A, B and C, D are perpendicular to the magnetic field. So let's make it perpendicular then. It is not looking perpendicular. So these are the magnetic fields. All this setup is kept on a horizontal plane. Yeah. All this setup is kept on a horizontal plane. So I'll draw like this. This is actually this is the case. Here two split rings are present like this. These are known as split rings, which are connected to brushes which are known as carbon brushes. So suppose this is split ring P, this is split ring Q, and these are connected to carbon brush X and Y. Through this carbon brushes, external circuit is present from which the current will flow. So X is connected to positive terminal and Y is connected to negative terminal of the battery, and this P and Q are the split rings. Yes, 3P and Q are the split rings. They are such like that they will move along with the coil. They will move along with the coil. These split rings will move along with the coil so that the coil will not get twisted. So that is the arrangement. So this is the direction of magnetic field, you know, north from south to, so from north to south pole. Yeah, from north to south pole. So what will happen? We have seen that whenever any current carrying conductor is present perpendicular to a magnetic field, whenever any current carrying conductor is present perpendicular to the magnetic field, then a force will act on it. Yes, a force will act on it, whose direction will be given by a rule which is known as Fleming's left hand rule. Fleming's left hand rule. So we will use the Fleming's left hand rule to decide the direction of current, or to decide the direction of magnetic force actually. If you can see, if I take this A, B, C and D. So if I close the circuit, what will happen? The current will flow like this from positive to negative terminal. It will move towards X. So from X, it will go from P, then AB, then CD. So now initially the direction of current is ABCD. Direction of current in the coil is ABCD. So if you can see, AB and CD arms are perpendicular to the magnetic field. Yes, AB and CD arms are perpendicular to the magnetic field, that is from north to south pole. So magnetic force will act on them. BC and AD, two branches BC and AD are parallel to magnetic field. So no force will act on them. Yes, no force will act on them. We already seen whenever the current carrying conductor is perpendicular to magnetic field, then only force will act. Yeah, and we have also seen a formula ILB sin theta. So here theta is 0 for the parallel sides, that is the angle between current and the magnetic field. That's why I'm saying the magnetic force on R0 on BC and AD. Now let's see AB and CD. So if you consider this AB side, what is the direction of current? Let's use the left hand rule. Yes, let's use the left hand rule. This setup is on the horizontal plane like this. This complete setup is on the horizontal plane like this. So what you can do, you can imagine it like this if you are getting difficulty in imagining. Suppose these are the magnetic north, magnetic south pole. These are the magnetic north and magnetic south pole. So this is the direction of magnetic field. This is the direction of magnetic field north to south pole. Now you can imagine easily. This is A, B, C, D. This is A, B, C, D. Now you can see the direction is like this. So if I make the direction of current, what is that left hand rule? FBI, force magnetic field current, force magnetic field current. So the direction of magnetic field is like this from north to south pole. The direction of magnetic field is like this from north to south pole. And the direction of induced current, direction of magnetic field is like this. And the direction of induced current is like this. So I'm arranging it like this. The magnetic induced current is coming towards you. Induced current is coming towards you, AB, and this is the magnetic field from north to south pole. So you can see the direction of magnetic force is downward. The direction of magnetic force is downward. So on the arm AB, the force will act in downward direction. On the arm AB, the force will act in downward direction. Clear? Now if you consider arm CD, what will happen? The direction of current will be like this from C to D. So if I align my middle finger in the direction of current like this is the magnetic field forefinger. The thumb is pointing upward. So that will show the direction of magnetic force will be upward on the arm CD. So if I take it a straight view or front view, on arm AB the force was downwards. On arm CD the force was upward. So it will make the coil to rotate in anti-clockwise direction. Yes or no? It will make the coil to rotate in anti-clockwise direction like this. So what will happen? This coil will rotate in anti-clockwise direction due to the magnetic force like this. So after half rotation, what will happen? After half rotation, I'm talking about situation when half rotation has occurred. After half rotation. So what you can observe after half rotation, now the CD branch will come here and AB will go down this side. Yes or no? So what will happen after half rotation? Let me add one more slide. Okay. Yes. So what will happen after half rotation? The situation is like this. The situation is like this. Now CD arm comes here, AB goes there. This is AB, this is CD. Okay. This was the split ring, and you know the split ring moves with the coil. So now this has become Q, this has become P. Because initially it was P. P is attached to arm AB. So that's why P comes here and Q comes here. But the carbon brushes are constant. So this is X, this is Y. And you know the current was flowing from X to Y. The current was flowing from X because X was connected to positive terminal. So now if you see, the direction of current will be like this. Yes or no? The direction of current will be like this. Getting my point? So the direction of current will be like this after half rotation. This is the situation after half rotation. Okay. Now the magnet is here, North Pole. This is South Pole. If you can see now again, now the current is flowing in arm DC or CD. So what will you do? You will again use the rule, Fleming's left hand rule, to arrive at the direction of magnetic force. So I align my middle finger in the direction of current, forefinger in the direction of magnetic field. So what will you observe? You will observe a downward magnetic force like this. You will observe a downward magnetic force. So what will happen? This was the case. Initially it was like this. AB, CD, AB, CD. The anti-clockwise rotation make the arm like this. So now this is CD, this is AB. Now again, if you observe this, CD is acted by a downward force, magnetic force like this, and this AB is now acted by a upward force. You can check the direction from Fleming's left hand rule for AB as well. If you take the direction of induced current like this towards me, direction of magnetic field is towards from north to south pole, then thumb will show the direction of magnetic force. Again, if you see it from front view, the CD arm will have a downward force and AB arm will have a upward force. So it will again make the coil to move in anti-clockwise direction. So after half rotation, there is some anti-clockwise rotation again. Due to that rotation, now the system looks like this after one rotation. The AB has returned to its initial position. The AB has returned to its initial position. Yes, and CD has returned to its original position again. This was again one complete rotation, and again the P will come here, Q will come here. P will come here, Q will come here. This is X, this is Y. This is X, this is Y. And you can see the circuit come back to its initial position. So this is the complete case of electric motor. That you can see during complete rotation. After half rotation, CD arm reverses its direction or replaces its direction with the AB arm, and you can see the force was acting on CD in downward. On AB it was upward, so again it rotated it anti-clockwise. So this makes a complete rotation. So this process continues. This process continues because after half cycle, what is happening? The direction of current is reversing. After half cycle, the direction of current is reversing with the help of split rings. With the help of split rings. Yes or no? Because split rings were moving with the arms, that's why it make the current reverse in the direction. So there is something known as commutator. There is something known as commutator. Commutator is anything which changes the direction of current. Which changes the direction of current with time. So here in the case of electric motor, split rings are acting as commutator. Split rings are acting as commutator because they are making the direction of current to be reversed. So I think the complete working principle of electric motor is clear, that how does electric motor works. There is some electrical energy supplied from the battery. Due to that electrical energy, current was flowing in the coil. And if the coil is present in a magnetic field, then it is acted upon by the magnetic force. So due to that magnetic force, a torque will act, which will rotate the coil. After half rotation, arms will be swept and it will again rotate in the anti-clockwise side and make complete one rotation. So due to this continuous rotation, so this electrical energy what we are giving is getting converted into mechanical energy like this. Rotation is mechanical energy. Okay, so this was the case of electric motor. If I talk about the real life motor or the actual motors which are used, in place of permanent magnets, we use electromagnets in that motors. We use electromagnets, and what we use large number of coils. I have taken only one coil ABCD, but yeah, there are large number of coils bounded. There are large number of coils bounded in the actual motors. Okay, so I think the concept of electric motor is pretty much clear. The whole concept of electric motor is clear, that how actually electric motor works. So what actually electric motor does? Electric motor converts electrical energy into mechanical energy. Clear? Okay. Now see second component or second electrical device, which is known as electric generator. So what is electric generator? It is a device which converts mechanical energy into electrical energy. Yes or no? What was electric motor doing? It was converting electrical to mechanical. Now electric generator is a device which converts mechanical energy into electrical energy. Mechanical energy into electrical energy. So that is a device. So it is written, a generator is a device that converts mechanical energy or motive power into electrical power for use in an external circuit. So we have already seen in the last class, by the process of electromagnetic induction, a current is produced, which is known as induced current. But the value of that induced current was so low. But yeah, it can be made large. It can be made large by increasing the number of coils. So that setup is known as electric generator, in which you are producing a high amount of induced current. We are producing a high amount of induced current with the help of process which is known as electromagnetic induction. So what is the principle of electric generator? Principle is that it works on the principle of electromagnetic induction. It works on the principle of electromagnetic induction. It works on the principle of, I am writing in short, EMI. EMI means electromagnetic induction, that whenever a conductor is placed in a time varying magnetic field, yes, or you can say the magnetic field is changing with time, then it will induce a current in the circuit. It will induce a current in the circuit or the conductor, that is known as induced current. Okay, so the device is known as electric generator. So you can see in this diagram here, there is a coil. Yeah, there is a coil which is continuously rotating, in a magnetic field. This magnetic field, this is a magnet given. Between the magnet, coils are kept. Between the magnet, coil is kept, and it is continuously moving. So you are giving it a mechanical energy. Due to that mechanical energy, what you are observing, you are getting some potential difference in the voltmeter connected in the external circuit. You are getting some potential difference reading. This is voltmeter. This is voltmeter, which is giving the reading of potential difference. So due to the movement of the coil in the magnetic field, you are getting some deflections or some reading in the voltmeter, which is showing that a current is produced. With the help of process which is known as electromagnetic induction. Clear? Now see what is the working of electric generator. Again, it consists of a coil like this. There is a axle like this, which will rotate the coil. There is an axle. On this axle, the setup is like this. At one point, it is connected. Suppose it is P, it is Q. Yeah, these are the known as rings. Now, in place of split rings, rings are present, complete rings. So one complete ring is Q attached to a carbon brush Y. One complete ring is P attached to carbon brush X. Now it is connected to external resistor. This X and Y are connected to the external resistor or a potential voltmeter, which will show the reading of voltage generated. So with the help of shaft, what you are doing, this is the axle. If you rotate this axle by any mechanical means, then the coil will rotate. This coil ABCD will rotate. So see what will happen. This is the magnetic field present. Here. So you know what is the property or what is the rule which we use to find the direction of induced current? That is known as Fleming's right-hand rule. So we will use Fleming's right-hand rule to decide the direction of induced current in the coil. Clear? So now if you see, the direction of magnetic field is from north to south. Yes. So suppose I am rotating this ABCD in the clockwise sense. I am rotating this coil ABCD in the clockwise sense. Means AB is moving upward initially. AB is moving upward and CD is moving downward initially. That is the clockwise rotation. So what you can observe, use right hand rule. What is the motion of conductor? Or I can say AB, motion is upward. So motion was shown by thumb. Motion was shown by thumb. So I'll point the thumb in the upward direction of my right hand. What is the direction of magnetic field? It is given by forefinger. And you see the direction of magnetic field is north to south. So the situation is like this. The situation is like this. Thumb is pointing upward. That is the motion of conductor. This is magnetic field, forefinger. So this middle finger will give the direction of current that is coming towards you or from A to B. Or from A to B. According to the figure, the direction of induced current is from A to B. Like this. Okay, now see arm CD. If I make the right hand rule for arm CD, what will be the case? The motion is downward. So the thumb will be like this, downward. Magnetic field is still like this. So you can see the middle finger is pointing towards me. Middle finger is pointing towards me. That is from C to B. So this is the actual direction of induced current in the circuit. That is from ABCD. That is from ABCD. If you can see, the current in the external circuit will go like this. Because this is the CD arm. CD arm is attached to Q and through Y. So the current will be like this in the external circuit. Got the point? So with the help of magnetic field or with the help of rotation of the coil, we have generated a current which is known as induced current in this direction like this, yeah, from Q to P. Now what will happen after half rotation? After half rotation, what will happen? Now the sides will be swept. Sides will be swept like this. Yes or no? So suppose the half rotation has occurred and the AB and CD side have swept. This is now CD. This is now AB. Okay. This is again axle. Now if you see, the rotation was clockwise. So now the rotation was clockwise. Now the arm AB will go downward and CD will go upward, if you can observe. Because initially AB was this, CD was this. The rotation was like this. AB moving upward, CD going downward. Now after half rotation, this is CD, this is AB. Now CD will go upward and AB will go downward to move in clockwise sense. So if CD is moving upward, what will be the direction of current? It will be like this. We have already seen from the right hand rule. So in AB arm, it is moving downward. So the direction of induced current will be like this. Okay. So what will happen now? This arm AB was connected to P. Arm AB was connected to P. Yes or no? And this arm CD was connected to Q. So if you want to observe the direction of current, this P was X, this was Y. So the situation is something like that. Yes, this is the situation. Yeah. This is the resistance. I have drawn external resistance. So if you carefully observe now, the direction of current in the external circuit will be like this. The direction of current in the external circuit will be like this. Yes. If you can see, why I am saying this, because this is Q, this is P. They have changed their position with the brushes. So that's why the direction of current is being reversed. The direction of current is being reversed actually. So what you are observing in the generator, first initially the direction of current was this direction. If I talk about the resistor, it was like this direction from left to right. Now it is from right to left. So after half rotation, the direction of current has been reversed. After half rotation, the direction of current has been reversed. So this reverse direction is something known as alternating current. This reversing of direction is something known as alternating current. So alternating current is that current which reverses its direction after a certain interval of time. Which reverses its direction after some certain interval of time, or you can say after every half rotation. So again, after half rotation, this CD is here. Now again, after complete rotation, AB and CD will swap their position and come back to the original position. So this process will continue to take place, and continuously some current is drawn in the external resistance, which is changing its direction with time. So we are getting alternating current. So this type of generator is basically known as AC generator. This type of generator is known as AC generator, which is producing an AC current or alternating current. Yes, there is something also known as DC generator. If you want a DC supply, means direct current. DC means direct current. Direct current means the current which does not change its direction with time. Yeah, so if we talk about the graph of direct current, it will be like this. It is not changing its direction with time. And if we talk about the alternating current, the graph will be like this. It is continuously changing its direction with time. So that is the difference. So if you want to use a DC generator, then use the previous concept we used in DC motor, electric motor, that is split ring. split ring commutator. Use the thing split ring commutator if you want the current to be in same direction. But if you want AC supply, AC current, that will be done by this setup. So in our house, in our homes, the supply which is coming is AC supply, alternating current. And in India, if I talk about, if India in AC cycle, 100 cycle is completed, 100 cycle every second. 100 cycle of AC is completed every second. That means the frequency of AC supply in India is 50 hertz. The frequency of AC supply in India is actually 50 hertz coming to your homes. So what is alternating current? The current which continuously changes its direction with the time. So I think the concept of AC generator is clear. What is its the principle? The principle of electromagnetic induction. That whenever a conductor moves in a magnetic field, then a current will be induced in that conductor, which is given by the principle electromagnetic induction. And direction we have decided with the help of Fleming's right hand rule. So we have basically revised all the three things. Yeah, we have revised the topic force on a conductor which was acting on electric motor. We have revised Fleming's left hand rule, which we were using in electric motor to decide the direction of force. Then we have seen AC generator, yeah, in which we use the concept or revise the concept of electromagnetic induction. And then we see how to apply Fleming's right hand rule to get to the direction of induced current. So I hope both the things are clear. Okay, now let's move forward. Now there's a question. Electric motor is a device. So you already know before watching the option even, you can see electric motor is a device which converts electrical energy into mechanical energy. So what is where is the option? This B option is here, electrical to mechanical energy. Yes, this is electric motor. Simple. Now see, choose the incorrect statement. These questions are pretty much to observe. You have to choose the incorrect statement. Yes, so read it carefully. Option A, Fleming's right hand rule is a simple rule to know the direction of induced current. Yes, correct. It is a rule to know the direction of induced current. The right hand thumb rule is used to find the direction of magnetic field due to current carrying conductors. Yes, this is also correct. We have seen right hand thumb rule. Yeah, right hand thumb rule like this. So it is used to find the direction of magnetic field. The difference between direct and alternating current is that the current always flows in one direction, whereas the alternating current reverses its direction periodically. That is also true. The direct current is that current which flows in one single direction, and alternating current is that current which is reversing its direction periodically. Okay. Option D, India, the AC changes direction after every 150 seconds. No, it is actually changing direction after 100th of a second. Yes. So this is wrong. This is wrong, that in India, AC changes its direction after every 100th of a second. Okay. That's why the frequency is 50 hertz. So I hope the concept which you have learned today, all the three concepts are clear. Fleming's right hand rule, electric motor and electric generator, all are clear. Electric generator is also known as dynamo. Electric generator is also known as dynamo. D-Y-N-A-M-O, or you can say AC dynamo. So I hope all the concepts are clear. Yes, thumbs up guys. So yeah, in case of still any doubt, what can you do? You can refer to the Ask IITians website. There's a doubt forum there. You can post your doubts here, which will be solved by the expert faculties there. Okay. So that's all from the session. Thank you so much. Stay safe and enjoy. Bye.